Uh, Hope everyone is enjoying the conference so far. Thank you very much for having me. It's a pleasure to be here. It's my first time in Korea, and I'm very excited to do this presentation for you all. So, as I mentioned, I am the COO of Aleo, but today I'm not actually going to be talking about Aleo specifically. This talk is really about kind of demystifying zero-knowledge proofs and focusing on the applications and really use cases for them. So. Yeah, oh, and one other thing I wanted to mention is I tried a new format for this slide deck, and I'm excited for this for a number of reasons, but if you want to scan this QR code, what you can do is you can actually find this talk on HackMD. So I wrote a version of this talk on HackMD, and HackMD is just kind of a simple markdown editor, an online markdown editor, and you can follow along and add comments anywhere, and you can see the exact content that I'm going to present here, and my hope is that this can be a community document that anybody can feel like they can comment on and potentially contribute to, and it can be a living document. And if anyone wants to take this presentation and have his notes later, so you don't have to take notes during the presentation, or if you want to give a similar talk yourself, feel free and use this. So, or feel free and follow along. Okay, so the motivation for this talk is, like I said, is not to focus on the low-level zero-knowledge cryptography. How the protocols work, how the math works, all that. The focus here, and by the way, I'm not a cryptographer. I'm the CEO of Aleo. My background is investing. I was at A16Z before, and before that, I was in the military. And there's plenty of people here who understand the low-level nuances of zero-knowledge cryptography. I would encourage you to ask them. There's tons of great resources out there. But the focus of this talk is really about the applications. I think we have a ton of work, including by some great teams like Anoma, who you just saw, Starkware. Aleo, the project that I work at, Zcash, it's a ton of great work on the protocol level for building these platforms for developers to create applications powered by zero knowledge. But there's not that many, unfortunately, there's not that many example applications out there. So the point of this talk is to really is designed, the audience is supposed to be for the developers out there who want to use this technology and apply it to real world problems. And so, the idea is to give enough context to be able to do that. Okay, so I'm going to start off by just kind of giving like a short run-through history of ZKPs, and I'm going to apologize in advance to anyone who's a cryptographer in the room. This is going to be a high-level presentation, so there's probably going to be some oversimplifications in there. And again, if you have any feedback on any aspect of this talk, the QR code, you can leave comments in there and everything, and we can kind of iterate over time. But the idea here is just, again, like give some context about zero-knowledge proofs, how they came about, and then transition into what I really want to talk about, which is the potential use cases for this technology. So here we go. Okay, so the motivating problem, and two cryptographers walk into a bar, not the start of a bad dad joke, although I am a big fan of bad dad jokes as a father of three. But this is really the motivating problem behind like these ideas that became zero-knowledge proofs. And it's not two cryptographers that walked into a bar, but it's two mathematicians. And the idea is basically that the mathematician A says to mathematician B, hey, I've just found this interesting result, and here's a proof, and hands the other one a proof. And then mathematician B, okay, how do I know this proof is correct without rerunning every step or re-executing every step of that proof? And the question that motivated this is like, well, can mathematician B verify mathematician A's claim without walking through it all the way? And so this is called interactive proofs. This is a class in complexity theory. And this is I basically just described the idea where you have two parties, a prover and a verifier. The prover hands a proof of some result to the verifier, and after some back and forth, the verifier accepts or rejects. On its face, it kind of just seems like a toy problem that wouldn't have really any applicability to anything that we'd care about. But it turns out that this paradigm can apply to a huge range of problems that we do care about. Okay, so here's the same thing in emoji form. So again, Alice makes a claim. Bob is allowed to ask Alice some questions, and they do this over the course of several rounds. And at the end of this process, Bob either accepts or rejects Alice's claim. And kind of one key piece here, which I already hinted at, is that the interaction or the transcript of this interaction is shorter. I'm just kind of hand wave what that means for a second, but it's shorter than the actual computation proven itself, because the trivial way for Bob to verify Alice's claim would be to redo everything. So that's not really interesting. What we're looking for here is some way for Bob to do it in a more efficient way. Okay, and so what are the key properties here? So the first one is completeness. So an interactive proof, system should have this property of completeness, which means that the prover, in this case Alice, should be able to prove anything within the language that Alice and Bob are speaking, and Bob should be convinced of it if it's a correct proof. And then soundness is this idea that Alice should not be able to fool Bob into accepting an incorrect proof except with basically negligible probability. And there's kind of one more question here that people started thinking about was, well, what if Alice could prove something to Bob without revealing anything else about the statement being proven other than the fact that it was just true or false? And this is this concept of zero knowledge. This is the first time that we really had this concept of like, hey, what if we added this property of zero knowledge? And this is really the first time that this vernacular came into being. And this is the paper actually that was published in 1985 by Silvio Micali, Shafi Goldwasser, and Charlie Rakoff that basically came up with this concept, right? So this is the idea of like, could the prover not reveal anything to the verifier other than whether or not the statement was true? Okay, and so, from this point, we basically kind of get, this is the journey begins for all these different zero knowledge proof flavors. So what I just talked about was interactive proof. So if you have these interactive proof system and you add this kind of zero knowledge property into it, you get what are called Sigma protocols. And a Sigma protocol, you guys may not know it, but probably many of you are at least familiar or have heard of Schnorr signatures or Schnorr protocols. So Schnorr signatures are being considered to be added into the Bitcoin protocol through the Taproot upgrade. And that's an example of a Sigma protocol. So it's an interactive zero knowledge proof scheme. And if you take a Sigma protocol, which is interactive, and you basically have this magic 8-ball to signify some randomness. If you apply this trick of, hey, instead of the prover interacting with a verifier, you have a prover that's effectively rolling dice or flipping coins to simulate what a verifier might randomly ask, then you can turn an interactive protocol into a non-interactive one. It's called the Fiat-Shamir heuristic. So if anyone's ever heard that, wondered what it meant, that's what it means. It's a relatively simple idea, but very powerful because now the prover can just can prove things to the world, to no one in particular, and make a claim that then anybody can come along afterwards and verify and say, okay, this claim is correct. And so if you mix this Fiat-Shamir heuristic and this randomness effectively with Sigma protocols, you get NISICs, and that stands for non-interactive zero knowledge proofs. And if you mix a non-interactive zero knowledge proof with, I'm just going to say magic. It's not magic, but it's not the purpose of this talk to go into what goes into making a NISIC a ZK snark. So I'm just going to hand wave that, but just understand that a NISIC, plus some special stuff is what a ZK snark is. And a ZK snark stands for zero knowledge, succinct, non-interactive argument of knowledge. Okay, so I'm almost done with the context setting, but I wanted to define these terms for all of you because in my journey in this space, in this industry, I've often found that people don't actually know this history and they don't understand what this means. And I think the context is important as you think about how to potentially apply it. So again, we have interactive argument, which is gets back to the beginning where we had talked about interactive proof systems. The non-interactive piece implies that the Fiat-Shamir heuristic is implied. We have some randomness that got kind of added in there. And the succinctness piece, the definition of succinctness and the variations on that definition are really what define or make up the different protocols, the different flavors of ZK snarks. So this is where you get the difference between Starks and bulletproofs, for example, and the traditional ZK snarks that Zcash uses, for example. The different ways that we define succinctness, and just I guess at a high level, the way to think about succinctness is that the size of the proof should either not grow or grow at a very slow rate compared to the program being proven. Okay, so again, just to wrap up the first section here, so let's kind of looking at the way these things have evolved. So again, we have the 80s that published the paper that I showed earlier was published. The 90s, we have the Schnorr protocol, which also itself was presented in a paper in 91. We have these things called probabilistically checkable proofs, which were of interest mostly in research in the 90s and 2000s, and that kind of led to the first ZK snark that was implemented in Web3 and Zcash, right? So in the first iteration of the Zcash protocol, they used this Pinocchio proof system, and then they later implemented to the first, I think it was the first hard fork in Zcash, this proof system called Groth16. So if you ever heard this term Groth16, it is named for the author of this paper that was published in 2016 about a specific kind of construction of a ZK snark. And so that was a real breakthrough because it was a huge leap forward in efficiency. And then that itself inspired a host of other interesting proof systems that do all kinds of different things. Okay, So that was the context I wanted to give you. So now I want to turn to like the real meat of the talk, which is what are they good for? So what's the purpose of these things? It sounds really interesting. We have these interactive proofs. You know, is this a theoretical thing or can this be applied in the real world? So I think the way I like to start by talking about this is thinking about like what's the real breakthrough here, and the simplest way is thinking about this before this technology existed. You had this kind of unbreakable tension between being able to verify something and being able to conceal information, right? So if, the simplest example that I like to use here is poker. Let's say you and I are playing a hand of poker and you claim to have a royal flush, right? And the only way that if you're playing real poker for you to prove that you have a real royal flush is to show your cards once the betting is over and the round is complete. And what zero knowledge proofs effectively do is to let you prove that you have a royal flush without showing your cards. And so that's really like the key paradigm shift that this technology enables, which is why I think it's going to be so transformational, not only in Web3, but even with traditional Web2 use cases. So effectively, in short, it lets you to not trust anyone, but you can verify and cryptographically ensure that whatever statement that you're being presented is true or false. Okay, in the Web3 context, at least with most of the use cases we see today, these typically break down, proofs, ZKPs are typically used in two ways. And that's because they both conceal and compress information. So go back to the definition of ZK snark for a second. So ZK, zero knowledge, implies you're concealing some information from a verifier or from anyone. And the succinct part of the ZK snark implies that, again, there's some compression happening. And so if you look at, we're going to get into some of these use cases, but if you think about rollups effectively, what a rollup is it's not actually concealing that much information, but it's using this property of compression to enable you to have a more efficient computation or a more efficient protocol. Whereas something like Zcash or Aleo, it's basically the point is to hide, is to enable users to hide sensitive data from any observer. And that's really the use case there. So concealment and compression. Okay, so now we've arrived to the listicle part of the talk, where I'm just going to kind of run through some of my favorite use cases for ZK snarks. And again, the hope here is to really try and inspire people to think through other use cases of this technology, which I think is going to be a potential breakthrough. Okay, so the first one that I want to talk about here is regulated stablecoins. So we have stablecoins. I think most people are familiar with the concept of stablecoins. I think one of the more popular ones is USDC, right? And the idea of USDC on Ethereum is relatively simple. You have effectively a blacklist where people can send tokens which are pegged 1-to-1 to $1 to anyone else who's not on the blacklist. And it's amazing. It's a breakthrough for many reasons. I mean, one of the reasons is that it makes settlement between parties extremely cheap, especially across border. So if I have a dollar bank account, I want to send somebody in Korea some money. In the traditional financial system, it turns out that's extremely complicated, but in Web3, as we all know, it actually becomes very trivial and much cheaper at scale than many in the existing rails that we have. Now, the drawback of something like USDC or any stablecoin that's issued on a chain like Ethereum or any transparent blockchain is that if you give me your address to send you USDC, not only do you reveal all of the assets that you currently own, but you also reveal everyone you've ever interacted with, right? And just think about this for a second in context of how the traditional financial system works. Like, not only is that not private, it's less private, it's much less private, right? And so there's potential reasons, especially when you talk about real economic use cases, businesses, supply chain, contracts, et cetera, that you would want to maybe hide some of that information. And so you can use zero knowledge proofs to create stablecoins that enable private transfers between parties. And this basically is what Zcash is. Taking it a step further though, you can also add logic like USDC has, where you have a blacklist or it could be even more complicated than a blacklist, some regulatory regime that you want everyone to comply with. And you use a zero knowledge proof as if you're transferring an asset on chain, you attach a proof that say, hey, I complied with this regime, with these constraints. And then this not only ensures to regulators that you're following the law, it also massively simplifies the problem of compliance for regulators or for banks, right? A lot of people may or may not know this, but some of the biggest banks in the world employ massive compliance departments that really have to do the manual job of sifting through transactions and understand, hey, is this a fraudulent transaction? Is this person laundering money, et cetera, et cetera. So again, I think the thing I like to point out here is ZKPs actually it's a two-pronged use case. It definitely helps. It helps on the consumer front, protecting your personal data that you don't want to reveal to everyone for all time, but it also helps regulators and does their job easier. Okay, cool. Another use case that I like a lot is the on-chain. I mean, everybody loves trading on-chain. You know, all these assets are, you know, basically assets that you can trade, and so there's liquid marketplaces such as Uniswap on-chain, and it's a great use case for crypto. I mean, the ability to access and move liquidity around quickly and automatically is one of the really powerful use cases on Ethereum, certainly. And but one of the challenging things for that, again, in the model of transparency, is, you know, if you want to do a large trade, there's potentially, you potentially could end up sending a signal to a market that you don't intend to send. And as a person who used to work at a very large venture capital firm that had big positions in various networks, you know, you could see a scenario in which, you know, hey, the fund cycle, it necessitates some sale of an asset, but you don't want to appear to be short of, you know, you don't want to convey to the market that, you know, you're not bullish on the future of it. And, you know, there's a whole bunch of reasons why people use OTC trading. In fact, in some asset categories, the OTC market is much bigger than like what's traded on exchange. And again, it's very difficult to do on a transparent platform like Ethereum. And so you need to kind of mix in to something like Ethereum or on another platform potentially, ZKPs to enable this use case where you basically have two counterparties who may not know each other, and the amounts to the world may be private, but you can do this, you can have the same on-chain settlement that you wouldn't say Uniswap, but in a way that would enable this specific use case. Proof of solvency. Okay, this one, unfortunately, is very relevant these days. I think we're all pretty familiar with, over the course of the last 3 months in crypto, all of the, I guess, scandals, blowups, issues that have affected various large protocols and or funds that have cascaded and kind of rippled throughout the markets. Of course, you know, initially we have kind of the issues with Luna and the peg breaking for that stable coin and kind of the ripple effects of that through Three Arrows Capital, all the way through all these large kind of quote unquote crypto banks, Nexo, Celsius, BlockFi, etc. And really the fundamental problem here is that the transparency, there was very opaque in terms of what the transparency and how, certainly at the larger funds such as Three Arrows Capital, how risk was being managed. And one of the nice things about zero knowledge proofs, again, it lets you break this paradigm of hiding something and verifying something, right? And so one of the advantages or potential use cases, I think, especially in light of these things, is a proof of solvency, right? So if you're running a fund or even a crypto bank, you can prove without revealing the positions of all your assets that these assets, you know, that you're able to, you know, meet all of your margin requirements, so that you're able to pay all of your liabilities or within some multiple of that. So you can encode all of that logic inside of a zero knowledge proof. And actually, this is not even a new use case. People first thought of this concept after the MT Gox hack several years ago. And this idea that, you know, how do you know that an exchange actually has enough reserves to meet its liabilities? And so there's some research out of Stanford, actually now several years old, that, you know, enables you to do that as an exchange. Say like, hey, without revealing all the on-chain addresses that we use, without revealing the specific asset positions, without revealing any of this other stuff, we can prove that we can meet all of our liabilities. So again, I think for DeFi, or especially for the intersection of where CeFi meets DeFi, what some people like to call CDeFi, these types of constructions are going to be extremely important. Okay, so kind of transitioning from a couple Web3 use cases to maybe something more familiar to at least people who are newer to the space is passwordless authentication. So probably some of you know that the way authentication works today is, you know, you have a password, you choose a password, and you type the password in on your device. There's a whole bunch of things that are supposed to happen in that protocol where you're authenticating to the server to protect your password to make sure it doesn't get stolen. The problem is, you as a user, not very often do you have control over whether or not all of those things were implemented or implemented well. And this is why there's all these hacks that constantly happen and exploits from credit bureaus and everything else, where it's like it turns out that these organizations weren't doing what they were supposed to do, and as a result, public information that should have been private became public, right? And so what this paradigm does, or the paradigm that I'm imagining for passwordless authentication is, you know, you basically authenticate by proving knowledge of something, that could be a password, without ever revealing like what the thing is. So there's never any reason to store it on the server, right? And the advantage of that from a user perspective is that you no longer have to trust anyone to do it other than yourself, right? So it takes the power away from organizations that maybe aren't incentivized to protect this information and puts it back into your hands. Self-sovereign identity is another big one. I mean, this one could be a talk all on its own. But for those of you who aren't familiar with the concept, self-sovereign identity refers to this idea where you basically, it's a digitally native identity, where you can take you can have these set of traits that define you effectively, and you can take those to anywhere on the web, and you can maybe just show selectively certain traits to certain people without revealing everything about yourself. And you can probably already understand how I just described that like it basically requires or it necessitates something like zero knowledge proofs, right? So if you want to take like another example that I like is if you want to go out to a bar and you want to prove that you're of legal drinking age, you go, you stand in a line, you show the bouncer, whoever's at the door, your ID, and what you're trying to prove is that you're over 18 or 21 or whatever the legal drinking age is. But in the process of proving it, you of course are revealing all of this personal information to the bartender, or sorry, the bouncer, and maybe it's not something you want to reveal. Now, in a real world interaction, I mean, is the bouncer going to read your address and come to your house? Probably not. But in the digital world, of course, everything can be scraped very easily. In fact, I mean, probably most of us in the era of COVID, or even just traveling, have had the experience of having to upload a passport to some website, and it's like you have no idea whether that information is being saved, what purpose it's being used for. So imagine a situation in which you could authenticate as a citizen of a country, say I am a US citizen, but I don't need to show you my passport. I don't need to scan and send this because now you have my passport number and potentially makes it a lot easier to impersonate. Private and secure voting. Another really big use case that I think is very applicable to DAOs. So DAOs today, most of them operate transparently where votes come up to adjust the protocol, et cetera, and people go ahead and cast their votes and and then the result is settled. But there may be situations which you want to have private voting. I mean, the obvious one is when we elect, certainly in the US, and I think most other places, when we elect our representatives, part of our democratic system, votes are counted manually by just an individual, and those names are not associated with votes. It's private. And so you may want to, in certain situations, in a DAO, for example, you may want to keep that information private. You may not want to tie people publicly to given votes, especially given that because these are blockchains, they persist for a very long time, right? So there could be a lot of interesting new constructions that we haven't yet explored for DAOs that zero knowledge proofs really enable in terms of the private voting. Private and secure blockchain-like clients. So this one, mostly I've talked about the utility of ZKPs in terms of this aspect of concealment of information. This use case is much more Web3 focused, and it's really focused on the ability for zero knowledge proofs to compress information, right? And so this particular use case is the idea that you can take a blockchain, what is a blockchain? It's a long series of blocks, it's a bunch of information organized into a long series of timestamp blocks. And if you get to and as new blocks are added, the state is updated. Well, what if you want to sync a new client to the chain? What if you want to download a wallet, or what if you lost your wallet and you want to re-download everything and make sure and kind of restore what you had before? Well, how do you know that you're getting the right blockchain? Like, who did you connect to? What's the trust assumption there? And it turns out, if you haven't looked into this, it's a really interesting question. It's not really it's very nuanced in terms of how do you know you have the right state of the world? And one of the nice applications for zero knowledge proofs is that you can prove recursively all the way back, block by block by block to the beginning, to know that you have actually the right version of history on your device without having to store the entire thing and rerun it all yourself, right? Remember back to the initial example that I gave with the two mathematicians, like how do you prove it without rerunning it all yourself? The way Ethereum works today, if you sync an archive node, you literally have to go and rerun everything yourself. And the advantage of this, like a zero knowledge proof-based construction, is that you can just have these proofs that kind of recursively are layered such that you are given the latest state and you know that it was computed correctly cryptographically. And there's already teams that are doing this. I think one team that I really like that deserves to be called out for this is Celo. So they have a super light client wallet. Mina does this too. So these constructions I think are really interesting, and I hope that the Ethereum community considers this for the future of their protocol as well. Okay, privacy preserving AI ML for health data. Okay, so most of the time, if you say AI ML and blockchain in the same sentence, people, or at least certainly roll my eyes because you're like, okay, lots of buzzwords, like what, do all these buzzwords belong together? But actually, I think ZKPs have a lot of utility, especially when it comes to protection of personal data in the context of AI ML. So think about advertising, right? So arguably the biggest use case by value of AI and ML algorithms is getting user data from browsing the internet, right? Browsing the internet, watching videos. This is exactly how TikTok works, right? So you watch videos on TikTok, that information is collected, AI, ML algorithms are run, and then you're served new content, right? Now, what's happening there implicitly is you're paying with your data, right? But there may be situations like I use the example of health data where you don't want to give anyone your health data, maybe outside of your doctor. But there could be huge societal benefits to giving access to healthcare professionals in general, access to this data. So potentially you could see a situation, I can imagine a situation or an application where you as a user run an algorithm client side based on your data, and then you produce maybe to use a simple example, like a linear regression where you give a slope and you give an intercept, and you don't reveal any of the points that line went through. And so you can kind of, in some ways, protect the data that you care about protecting, but still get some utility from it. Okay, player-owned games. Actually, this is one of my favorite use cases for Web3 in general. There's so many cool ideas that are floating around out there. And I know Korea especially is really a hotbed of the latest in game development. And I think the opportunity for player-owned games in crypto and Web3 is so exciting because you can imagine a world in which a game that you really love, you also are a part owner of, and you have a stake in being able to vote for whatever new features or rule changes happen. And that's not a zero knowledge thing, that's just a Web3 thing. That's really cool. What zero knowledge enables that you can't necessarily get on kind of just in the regular sense or in the traditional Web3 setting is you have this ability to introduce this hidden information component to gaming. So I think there's a great game that I highly encourage everyone to try on Ethereum. Actually, I think you play the game on Gnosis Chain, but it's called Dark Forest, and it uses zero knowledge proofs to hide information about everyone's moves. Super interesting. And basically, it's the difference between playing chess and playing Battleship. Playing chess, chess is a fun game. There's no element of hidden information. Battleship, you can't play Battleship without hidden information. It just doesn't make sense. The whole point is to guess where someone's pieces are. So zero knowledge enables this class of games and potentially augments what's already, I think, a really exciting use case or category. Okay, I'm gonna start skipping ahead because I'm running a little low on time. Okay, so I just told you about how awesome all these zero knowledge proofs are. So why isn't everyone just using them already? We talked about, we thought of this in the 80s. Why are we still here? Okay, so it turns out there's some complications and some challenges, right? So one of them, and you may have remembered a couple weeks ago, there's a lot of announcements, and maybe I think a few people talked about it today, is you have to ZK EVM, so making this compatible with the EVM. Very hard problem and not trivial at all to solve. And so that incompatibility with existing models remains a challenge for this technology, but I think we're getting better and approaching ways around that. Lack of tooling. This one I think is much closer to being solved. For example, at Aleo, we have a smart contract language called Leo, which basically lets anybody write high-level JavaScript-y syntax, which compiles down to R1CS, which is kind of the low-level stuff that proofs are made of. And before that, you had this kind of, you had to basically hand make all these things in a very, time-consuming way. There's some performance overhead, which I already talked about, and then data availability. The data availability problem is just ensuring that whoever needs to generate the proof has access to the right data. Okay, what does the future hold? So I hope the slide I showed a little while ago about how the space has progressed has convinced you that there's just an exponential growth in new techniques to solve all the challenges I just laid out. Better tooling and language support is coming. Hardware acceleration, actually the t-shirt I'm wearing for Z-Prize, this is an initiative that I help run and is, consists of 32 teams across the space. The whole idea is to incentivize hardware acceleration of a lot of these low-level algorithms to make the real-world human time or the real-world human cost of these things lower. And so we're getting to the point where a lot of these things feel like they're far away today, but we're rapidly advancing towards solutions. Okay, in the last 30 seconds, I'm going to leave some closing thoughts. Okay, so zero-knowledge cryptography helps us overcome the tension between verifiability and privacy. I already went through that, but I think this is the big takeaway. If you take nothing else away from this talk, I think this is what I want you to take away. And I think, I've been talking mostly about use cases in the Web3 context, and I think it's just important to note that there's a lot of ways to apply zero-knowledge cryptography, both inside and outside of Web3. But I would encourage people to remember that the value of decentralization in Web3 is extremely important. And the way that these zero-knowledge proofs are applied, I think, should be used to empower users and ensure that decentralization remains a core principle that we uphold, as opposed to the opposite. Because there are ways and there are companies out there that don't actually hold that to be a core value. So I think it should be. And I guess moving on from there, I view Web3 as a quantum leap forward, but I don't think we can all, as a species, just take for granted that we're constantly going to be advancing as time passes. And I'm a little bit of a technological utopian, so I believe that as we get better in new technology, life will get better, but that's not guaranteed. And it requires the work of everybody, including many of the researchers whose work I referenced in this talk, many of the people who are here presenting, how their zero-knowledge proof systems are going to make the world better, and all of you potentially who can contribute to the space or who are even here to learn about it. It takes all of us together to push these boundaries forward. And lastly, I'll leave on this note. If you want to get involved and you want to start learning more, there's never been a better time. This is truly the beginning of the beginning, and I highly encourage you to do some research. In fact, if you go to this QR code, this is the end of my talk, but if you go to this QR code again, there's a bunch of resources in there. I would encourage you to add more. And again, we should consider this talk that I just gave a community resource that I encourage all of you to take and use as you see fit. Hopefully this was helpful. Thank you all very much.